Decision tree is a type of machine learning model. It represents the model in a tree of nodes. The nodes are decisions based on a feature of the data, and the leaf node represents a prediction. Here is a very simple example. This is a binary classification problem to predict whether a customer will buy or will not buy. And there are two features involved. One is age, the other is the gender. So given a customer, based on this decision tree, we can get a prediction whether the customer will buy or not. So the first feature is to look at the age. If the age is greater than 20, then look at the gender. If the gender is female, then will not buy. The decision tree model is represented by a tree of nodes, so it's very easy to interpret a decision tree model, which is one of the advantage for decision trees. Also, decision trees are flexible. They support both categorical and continuous features, and they can be used for both classification and regression problems. Given the training data, how to construct a tree? The tree is built in a top-down recursive divide and conquer manner. So all the training data is first put in the root node, and then in each step we find the best feature to split the data. For example, in step 1 from the root, we find a best feature A, and when the feature A equals true, we split the data into subset data 1, and when the feature A equals false, we put the data into data 2. Then for each subset, for data 1 and data 2, we further find the best feature in the rest of the features to further split the data. So for data 1, we may find the best feature C, and for data 2, we may find the best feature F. So that step by step, we split the feature one step by another, and until the node reaches the termination condition, then we stop at the and set those nodes as leaf nodes. Formally, the decision tree algorithm is as follows. The training examples are all at the root, and then recursively in each node, we select the best attribute that can best split the data, and then partition the examples according to the selected attribute. And when the termination condition is true, we stop the algorithm. MLlib has the decision tree class, which we can use to train a decision tree and then predict the test data. It has two methods for the classification and the regression problems. They are called train classifier and train regressor. Those methods have some major parameters. The data is an RDD of label point, and number of classes is to specify how many classes are there. This is for classification only. And the impurity is to identify the approach used to determine which feature is the best split, and we will talk about the impurity later. Max depth. Max depth is used to to specify the maximum depth of the tree so that the tree won't become very large and that will make it work well on the training data and cannot perform well on the testing data. And the maximum number of bins to split the data and the categorical feature info. This is to specify which features are categorical and which are not, and also the information about the categorical data. So this one we will also talk about in detail later. When we select the feature in each step, we want to find the best split of the data. Then how to define this best split? For example, if we look at these two examples, one example uses x1 as a feature to split the data. The other uses x2. So their root nodes all include 100 examples with 50 of them having labels of true value and 50 false. Okay, with x1 as the splitting feature, it splits data into two subsets. One subset has 20 examples with true labels, 30 with false labels. Another subset has 30 true labels, 20 examples with false labels. Then on the right-hand side, with using x2 as a feature to split the data, we got a subset of 50 examples with true labels, and the other set has 50 examples with false labels. Then which one is a better split? x1 or x2? x2, right? Because using x2 to split the data, it generates two subsets that are pure. These are two pure subsets. So the purity is a way to measure whether a split is better. So if the subsets after the splitting are pure, then this is a better split. Node impurity is a type of approaches to measure the homogeneity of the labels at the node. In MLlib, it implemented three approaches for impurity: twofold classification, including the Gini impurity and entropy. And one is for regression, which is variance. Given an impurity measure, the information gain is the difference between the parent node impurity and the weighted sum of the children's node impurities. With pure children's, then the information gain of this using the corresponding feature will have higher value. Then when we choose the best split, we want to have the purest subsets after splitting the data into the children nodes. Then the feature with the highest information gain is the best feature that can generate the purest set, which will be chosen in each step. This categorical feature info parameter specifies which features are categorical, and this is given as a map. Um, for example, in this example, it's a map from 0 to 2, 4 to 10. It means that the first feature at position 0 is a categorical feature, and it has two values. And at position 4, the feature has 10 values. If the feature is not included in the map, then they are treated as continuous. And this map can be empty. That means all the features are continuous. With categorical features, we can treat them as continuous values. We do not specify them in the map, but that will even though the decision tree can work, it's not as efficient and effective as specifying them explicitly as categorical features. So it's highly suggested to specify the categorical features in this parameter. In decision tree, the continuous feature is first processed to find the best split for this feature, and then this feature is compared with all the other features to select the best feature for the split at the node. With a continuous feature, we first rank the data by this feature, and then find the candidates to split the data, which can be found as the values that the label changes. For example, here from the first example to the second example, the label changes from true to false. Then the average of 10 and 5 will be selected as a candidate. Then also from 5 to 3, the label changes from false to true. So the feature value of 4 is also a candidate. Then from 3 to 2, they are all true values. So we don't consider these two values. And then from 2 to 1, there is a change in the label. So 1.5 is also a candidate. Then we have a candidate set of 3 values. We calculate the information gain to use them to split this feature, and the candidate with the highest information gain will be chosen as the split for this feature. And this information gain is this largest information gain is the information gain for just this feature, and it will be used to compare with the other features. In MLlib's implementation of decision trees, there are 3 parameters for terminating the algorithm. One is the maximum depth. A deeper tree is more expressive. That means it can include more information and potentially with higher accuracy. However, they are more likely to learn too much information on the training set and cannot predict well on the testing set. This is called the overfitting problem in machine learning. Another parameter is the minimum instance per node. This is to specify the number of training instance a node has to include. So with a lower minimum instance per node, then the tree will tend to have more leaf nodes. And similar to the depths, if a tree has a more complex structure, then it tend to be overfitting. And minimum information gain. This is another threshold to determine in order to split further, the split must improve the information gain by this amount. If any of the termination conditions satisfies, then a node will stop further splitting. Then it will be treated as a leaf node. These conditions are corresponding to the 3 parameters on the last page. So one condition is the depth is equal to the maximum depth, and another is there is no split candidate lead to an information gain greater than the minimum information gain, and no split candidate produce child nodes have at least the mean instance per node training instances. Here is an example. To load the data into an RDD of labeled point and then split the data into training and testing sets, and train a decision tree model on the training data and predict on the testing data. Here, the libSVM data is a type of commonly used data, and it can be loaded to an RDD of labeled point directly. And in this decision tree.train classifier, we specify the data as the training data and the number of classes equals 2. The categorical features info is empty. That means all the features are continuous. And the impurity approach used is a Gini, and the maximum depth is set to 5, the maximum of bins set to 32. A little bit about libSVM, which is another data format supported in MLlib. We can load an RDD with label points directly from libSVM dataset. libSVM is a commonly used format in machine learning, which represents the sparse data. Here is a format for a row in libSVM. The first column represents the label, and then the rest of the columns represents the indexes of the features column, and then the value of the features. The index of the features starting from 0 to the number of features, and in each row it only shows the features that have non-zero values. So the index 1 may be 100, index 2 may be 125. Here is an example file in libSVM format. This is a binary classification problem with labels of zeros and ones. Then the rest of columns are the features and their values. Random forest. In order to improve the accuracy and the robustness of decision tree, random forests are proposed as ensembles of decision trees. So instead of using only one decision tree, multiple decision trees are built based on different feature sets of the data. And then for an instance, the prediction on each tree will be generated, and the combination of their results are returned to predict this instance. If this is a classification problem, then the predictions are aggregated using a majority voting. For example, if we have 3 decision trees in the random forest, one of them output class A for an instance, and the other 2 output class B for this instance. With majority voting, then this instance prediction will be voted as class B. Since it's composed of multiple trees, this algorithm is called random forest. We can train a random forest model directly in Spark. Here is an example. Here we specify the number of trees in the random forest as 3. In Spark, since the data is distributed, the algorithm should avoid the large amount of data transmission. So Spark has 3 optimization strategies for random forest. The first one is the cut point sampling. This is especially for the numerical values. When we are treating the continuous values, we rank the data according to the features, and then find the cut point in the 2 neighboring values. This in a distributed environment, the sorting the data will lead to large amount of computational complexity. To avoid this, when Spark is building the random forest, it will sample in each data node, and then aggregate the statistics to get the cut point. The second strategy is the feature binning. So in decision tree construction process, it is to divide the feature values, and we will if we have m values, then there will be at most 2 to the power of m minus 1 partitions, and this partition will be analyzed from the data, and the feature will be binned, and only the bins are considered in calculating how to select the feature to find the subsets. And the last approach for optimization is level-wise training. So basically, decision tree is constructed using the recursive approach. On a local machine, when we are building the decision tree, it will move around the data to move the data for the same node together. However, this will not be efficient in a distributed system because the data set is too large to be placed together. So under this distributed environment, the strategy is level-wise training. This is to go through all the data and calculate and compute the statistics of the data, and after all the data in the same level is computed, then based on the features determine whether to split and how to split the data.